Hello world! In this tutorial series I will be talking about hidden Markov models, and what we want to do is try to cover the theory and implement some code in vanilla Python to make sure that we understand everything well. I do not have a master plan for this whole series yet. This is quite experimental, but we will see how long it goes along the way. Now here I will follow along the lines of a great classic paper by Rabina and colleagues, and I will try to stick to their notation as close as possible. So if you're interested in more background material or simply want to review what we do here, please fire up Google and search for it. Okay, but now let's get started with discrete Markov processes. These kind of models can be used to better understand the time evolution of systems that contain a discrete number of states. So what do we mean by that? So a system can be really anything, but to be concrete, let's think about weather. For such a system, it might be reasonable to define states such as rainy, cloudy, or sunny. To later save some writing, we will denote each of the state with a capital letter S, and we will index S with a unique number. So rainy would be S0, cloudy S1, and sunny S2. Now, a very useful representation for discrete Markov processes is given by circles and arrows, and we will use these diagrams to better understand our model. So, in this representation, circles represent states. So for our weather system, this could be S0, S1, and this one is S2. Now the second important property of discrete Markov processes are that we have some notion of discrete time. To indicate time, we will introduce a new variable t, which ranges from 0 to capital T, which denotes our final time step. Now during each of these time steps, our system has a state, that is either rainy, cloudy, or sunny. To denote the state of our system at time t, we introduce the variable lowercase q and index q with the time. To be a little bit more concrete, if we want to say that on day 0 the sun shines, we will denote it as q0 equals s2. Similarly, if on the next day, that is q1, the sun still shines, we would write it as such. Now, as the time progresses from one time step to the other, our system may or may not change its state with a certain probability. For example, here we saw a state transition from a sunny day to another sunny day. To indicate this in our diagram, we would draw a self-arrow such like this. And the probability for this to occur could be 0.8. Now, if on the next day, that is Q2, we observe rain, that is S0, we would draw this in our diagram as an arrow that points from S0, S2 to S0. And this could have the probability of 0.1. So what does the Markov property imply for our system? So consider that we observe the sequence sunny, sunny, and rainy on day 2. Consider that we are interested in calculating the probability that it is rainy on day 2. Given that we had 2 sunny days in a row, we generally would have to include the whole chain history in order to do so. However, here comes the Markov assumption into play, because this allows us to truncate this expression such that the probability of Q2 being S0 is only dependent on the observation of the day before. So that is Q1 equals S2. In other words, the probability of observing state J at time t is conditionally independent of the chain history given the state at time t minus 1. This is a strong assumption, however it is quite convenient as it allows us to simplify our calculations significantly. The next assumption that we are going to make is that the transition probabilities in our discrete Markov process doesn't change over time. If this is the case, then we can represent the transition probabilities in form of a matrix, in which each entry, Aij, corresponds to the probability that Qt is Sj, given that Qt minus 1 was Si. So if we want to draw the matrix that would correspond to our system over here, we would denote it as such. So the first entry here would be A00, and that would correspond to the probability of 0.4, because this is the state transition from S0 to S0. S01 indicates the transition from rainy to cloudy and would therefore be 0.3. Similarly, S02 would indicate the probability of jumping from a rainy to a sunny day. So one thing to notice that this is a matrix full of probabilities, and therefore each entry of this matrix has to be greater or equal than 0. And the second property is that each of these rows, they sum to 1. So the last concept that I want to cover before we actually go on and write some code is the initial state distribution. This is nothing else but a vector, let's call it pi, that contains the probability for each of the states at the first time step. So, in other words, that will be Q0, S0, Q0, S1, this would be Q0, S2. So with the initial state distribution and the transition probability matrix, we have enough tools at our hand to simulate our first Markov process. Okay, so now what we want to do is to take what we have learned about the initial state distribution and the transition probability matrix in order to come up with a function that will deliver us a chain, a discrete Markov chain. So to get started, we will first import NumPy. The first thing that we have to do is to define the initial state distribution. So this is pi. And let's say that each of our states, cloudy, rainy, and sunny, have equal probabilities. So that will be 1/3. All right. Let's define now the matrix A, the transition probability matrix. And what I will do is now to copy that from something that I've already prepared in order to save some time. So this is now a two-dimensional matrix. If we have a look at it, each row sums to 1. So we can check this by typing that. Okay, let's define now the function that will simulate the discrete Markov chain. This function will take 3 arguments, pi, which is the initial state distribution, the transition probability matrix A, and the number of time steps that we want to simulate. The first thing that we have to do is to extract the number of states, which we can simply do by checking the length of pi. Now, the first thing that we want to do is to sample Q0. And we do this by invoking the numpy random choice function. This function takes as a first argument an array that contains our states. So that will be 0, 1, 2. But to make the function work for other entries, possible entries as well, we will say numpy arrange n. And the second argument is p, which stands for probabilities. And here we will take pi, because this is our initial state distribution. Then let's define a list chain that contains Q0 as the first entry. Now we want to iterate along all the time steps. In each of these iterations, we want to sample now the next state of our chain. And we can do this by again invoking the numpy random choice function. Again, we will have to pass an array for the probabilities, but this time we will use the transition probability matrix, which row we index by taking the last state. And the final thing that we have to do is to append Qt to our chain. Then we will return it. So let's try our function. Let's simulate 5 steps. And alright, this would be our Markov chain. So we have sampled state 1, which would be cloudy, cloudy, sunny, sunny, cloudy.